Hey guys, I'm Dave Fetterman. I'm an engineer here at Facebook, and welcome to the second of the Facebook Tech Talks. I've actually recognized some of you from the last talk. The last talk was on chat, Facebook chat, and how we built that in here. And that's something that demonstrates a lot of the things we do on the application layer, the design layer. And this time, we're actually talking about something that's really crucial piece of server-side programming, or so systems Facebook run, and that is Memcached. So Mark is going to be talking about Memcached here in a sec. Just so you know, if you can read through the squigs, we got a Facebook Tech Talk page, so that if you guys want to see the next ones that are coming up, look at videos from old talks, post, do all that great social stuff that Facebook's so good at, you can actually go search for Engineering Tech Talks on Facebook, become a fan of that page, and get all these updates. So without further ado, Mark Zuckerberg on Memcached.
So today I'm going to talk about Memcache. The last tech talk that we had on chat seemed like a lot of fun, so I just figured, all right, I'm going to do one of these. I haven't coded in quite a while at Facebook, but one of the last things that I did was I implemented the first version of Memcache. So it's become a really integral part of our just the software stack that we use here. And one of the things that has been one of our biggest contributions back to the community. So I just figured this would be a pretty good thing to talk about. On top of that, Facebook is a technology company, and what that means to us is that just all throughout the company at different levels, including, obviously the engineering and operations and all those teams, but also just the management and the folks who are running the company, we think it's really important that they're technical as well, right? So I think that the fact that a lot of the decisions that we've made along the development of the company have resonated and kind of been in line with the technical strategy and what we're trying to get done in the world, just make it so that the whole company is just a lot more coherent. So today I'm going to talk about Memcache, which is just one part of what we're doing, and I think it has some really interesting problems. And if you're interested in systems or interested in working at Facebook, I think this is a good example of the type of thing that we do and the type of scale that we're dealing with. So just to give a quick intro to Memcache and why it's important for us. So on Facebook, what we're basically trying to do is help people share more information with the people around them, right, and the people that they're connected to. So the data set and the data access patterns that we have are different than from a lot of other types of applications, right? So if you take something like email, all of the data for a user can be stored in one place. For Facebook, a lot of the different applications that we have are pulling data from all of your different friends, right? So if I search for Dan, I'm going to get completely different results than if Dave searches for Dan. If I look at newsfeed, it's going to pull from a lot of different ones of my friends. It's going to be different from anyone else's newsfeed, right? Just kind of generated on the fly. So, the data access pattern is different, and in order for this to work, we've needed a fast cache and just a good way to get access to the data very quickly from just all the sharing that's going on. So the characteristics of Memcache that have made it an important part of what we do are, first, it's this distributed in-memory hash table service, right? So it basically runs across a whole cluster of machines, and you can have as many machines as you want, and basically really simple to set keys, get a lot of keys at the same time from all of your friends if you're pulling data from multiple connections that someone has from different machines, things like that. It's extremely simple. Basically what it does is it'll store data that is commonly used or hot from the databases in order to make it so that you can access it more quickly. So here's an example of some of the syntax, right? You can get as many keys as you want from a lot of different friends or people that you're connected to. That's really important to be able to pull data from different people where the data is on different servers. Set, really simple, delete. So just kind of how this fits into the stack, right? We have web servers, tens of thousands of servers, and basically the numbers aren't accurate here, but the web servers are doing around 50 million requests a second to Memcache, and just all like through the whole tier. And so what we found pretty early on, and one of the motivations for doing this was we found that even really fast database queries would still take a few milliseconds, right? So 2, 3, 4 milliseconds. And in order to be able to get this to work at good scale, Memcache queries take, on average, a little less than half a millisecond. So we have about a 95% hit rate in the cache. So most of the queries just go hit the Memcache. They don't have to hit the databases. It's one of the things that makes the infrastructure work. So this has become a really important part of the stack that we're using, and also for a lot of other companies. So how we're using it. We integrated this very early on. Our first integration was in, implementation was in early 2005, where from what we can tell from the different people in the community who are using this, by far the largest implementation of this. And the memory that we have is around, it's 20 plus terabytes, almost 30 terabytes at this point. And we've encountered scaling challenges that a lot of people haven't seen yet. So as we solve these problems, and we'll go through a number of them today, what we do is we just try to make them available to the community. And some of them we've been able to successfully merge back into the open source, the same branch of Memcache. Some of them we're in the process of releasing or have released in just our own branch. So, but you know, all the changes that we're making, we're releasing back to the community for other people to use if you're interested in this as well. So, okay, so now we're going to go through. I haven't done most of the stuff that we're going to talk about today. I'm going to highlight the work of a lot of really talented engineers at Facebook who have done different optimizations. The first part is what I did. So, so that's me. I did the very first implementation of Memcache in 2005. And just to give you a sense of where Facebook was at the time, there were a few people who worked for Facebook. Myself, Dustin, just a couple of early people. We didn't have an office yet. We rented an apartment in Menlo Park and just sat around a kitchen table and coded. And one weekend we were talking about how do we optimize the databases in order to make data access faster and continue to be able to generate all pages in faster than 200 milliseconds, right, which is just a goal that we've had. And so what we did was we kind of decided, we looked at some things that were available, including the early version of Memcache that had been built by the folks who started LiveJournal. It was just really basic back then, and we decided to implement this. And you know, me and a couple of friends who were working on Facebook then basically implemented the first version of this in a weekend, right? And that's just kind of fitting with Facebook's style of doing things. Go really quickly, move fast, iterate a lot, and just kind of solve the problems as they come up. So that was kind of the style that we had with this. So, so what I'm going to talk about isn't the first implementation. That's not that exciting. What we're going to talk about is just how it's evolved over time and the different issues that have come up. Right? So the first set of issues, Scott and, well, we'll just go with Scott for now. I think there was supposed to be someone else who's apparently not getting credit. Andrew McCollum, one of the early folks from Facebook. So, are these the right slides? Yeah. All right. Cool. So, the first set of issues, I mean, when we first got Memcache, it was in a really rudimentary state, right? So, all kinds of different issues. For one thing, it only supported 32 bits. So, so for among a number of other reasons, it just kept crashing, you know, all the time. And one of the biggest causes of this was, you know, the servers that we were running at had more than 4 gigs of RAM, and it being only 32-bit couldn't address that. And as it started using more of the RAM, it just overloaded and crashed. And this was just kind of like the first issue that we had, right? So apparently no one who'd used this before had ever used it on a server with more than 4 gigs of RAM. So, so this is kind of the first in a long sequence of things that we fixed. So I mean, the first implementation that we did, just kind of in keeping with a very fast hacker style, was just to write a script that would restart Memcache every 15 minutes because it would crash. And you know, it was still useful for those 15 minutes. But pretty quickly we made it so that there's McCollum. Okay. So quickly we made it so that we could actually support the 64 bits and that would work. Yeah. So then we started getting to some more interesting things. It was pretty buggy. So I can actually read this because of the angle. So there were all these issues early on where, you know, you'd send servers requests, and sometimes if a server had crashed, then the server would just keep on getting all these requests, even as it had just started coming up, and like the frequency of all the requests would overload it and just prevent it from ever coming up again. So just things like this that just kind of hadn't been thought of in the first implementation, that we were just working through these one by one, and everything up to the point where, the first client was written in PHP, and PHP serialization is pretty slow. It's, I guess, uses just straight binary, so like for serialization. So things like, okay, that's not, the data that I had there isn't there anymore. So things like a timestamp, which could be demonstrated in a smaller amount of time of memory, ended up being like taking up twice as much memory. PHP serialization also tends to be pretty slow. So when we first implemented the client ourselves, we were actually able to get it to go a lot faster. And this will be a theme of a lot of what I'm talking about today, because at the scale that we were operating at then, some of these things just made it so that it was faster and a lot more stable. But now that we have, I think it's almost 1,000 machines running Memcache, these small tweaks save the company millions of dollars. Right? So things that are really interesting edge cases that we run into, being able to detect these and kind of troubleshoot them and look through these have a really meaningful impact. And that's only possible because of the scale at which Facebook is operating today. So there are a ton of different things that we did with Memcache, but I want to focus for a little while on two of the more interesting architectural things that I think we've done over the past 3 years of using it. So the first was we ran into this issue. Well, it was a series of issues that basically made it so that we wanted to stop using TCP to transmit the data between Memcache and web servers, and instead we basically implemented it in the application in UDP. Right? So there were a number of reasons why we wanted to do this, and Mark is the one who did this, and he's there, so he can raise his hand. And also, these folks will be around to just answer specific questions on this stuff afterwards, so we can have a cool discussion about that. So there were a bunch of issues with this. So one issue was just that we had all these different connections going on, right? So if you picture, you have a lot of different web servers, which each have a number of different threads on them, right? Like in the web server. Each of those threads has a persistent connection to each Memcache server. So it ends up being, I think, almost 10,000 connections or so on each web server, but on the Memcache servers it was even more. It was, I think, hundreds of thousands of connections. And keeping those connections open required a bunch of memory. I think from some of the data that we had, it was almost 5 gigabytes. And for a cache whose job it is to efficiently use memory, that's kind of a bummer, right? You want to use the 5 gigabytes not for keeping the connections open, but for actually being able to store things and serve it quickly. So what we wanted to do was, I figured, instead of having all these different connections, we could just use UDP to transmit stuff. UDP means never having to say ACK. That's a awesome joke. No joke. So just to put this in the perspective of the type of problem that is pretty unique to Facebook and the data access patterns that we have here, and probably social networks in general, is on a given page, you're getting data from a lot of different friends, or people that you're connected to, in order to pull that together and show either recent events that all your friends are going to, or recent status updates, or things in newsfeed. And one of the things that happened over time is, just as people's friend lists grew, and there started being a few users who had thousands of friends or a lot of connections, there started to get some really big multi-gets, right? And the issue with TCP on this, which was another motivating factor for why we wanted to switch to UDP, was we'd basically we'd batch all of these different GET requests to the different Memcache servers, and we'd send them out to hundreds of different servers, and then they'd all just come back in and bombard the server that had sent them out initially. And the server, if it dropped the packets, then TCP would then require 250 milliseconds in order to retransmit, right, and get more data. But through using UDP, we were able to get around that limit, and that made it so we could really optimize the amount to which the servers could just send all the data back in response to the request. So using UDP was it was a pretty big project that took a while for Mark to get running, but it ended up being able to optimize all these different things, right? So memory use, and yes, in terms of just being able to transmit more efficiently. So we have, so you have UDP. There were other projects that we had at the same time, which the connection limit was a pretty big scaling thing that we ran into early on, right? And I mean, the first way that we knew that we had this issue with the number of connections was just that Linux had some limit where you physically couldn't have any more connections. But you can go into the kernel and tweak that, right? And there's a reason why it's there. You probably shouldn't tweak it that far. But so that's why we had to do all this stuff to get around it. But this was a pretty big problem. So we knew that the UDP thing would take a while to get done. So at the same time as we were developing that, we also developed this other piece, which is basically a Memcached client, which we call Memcached proxy. And I think that this is just a pretty interesting example of just a part of the Memcached ecosystem in terms of the deployment that we have that became interesting, not just for connections, but also for how we scaled out to multiple data centers and replication. So if you take a look at, that's the stack that I showed before, right? And this is basically, so you have web and then make requests to Memcache, and the ones that miss can go to the database. The way that this scales to multiple data centers is a little tricky because you need to keep the Memcache tiers basically need to be coherent with each other, so they're not just like out of sync or giving bad data. But at the same time, you need the Memcache servers to be close to the web servers, right? Because if you go back to the original reason why we implemented Memcache in the first place, to save that 4 milliseconds from the optimized database call to instead just go to the half a millisecond Memcache call, having 2 milliseconds of latency between a web server and even just another data center that we have in the Bay Area was just not acceptable, right? And the site wouldn't work with that. So the basic architecture that we have set up is we have the Memcache tiers with the web servers. For the small percent of misses that we have to the cache, those can go to the database because they're only 5, 10, 15, maybe a page, right? So that's not quite as big of a deal. But keeping the Memcaches, the tiers coherent with each other was a big challenge. So we basically were able to use Memcached proxy as a solution to this. So basically, just to go through what Memcached proxy is, instead of having all of the different connections, right? So instead of the UDP solution, right? So that was one of the solutions that we had to this problem of a lot of connections. An alternate solution would be to have all the different threads on a web server instead go through one single Memcache client, which maintain persistent connections to all the different Memcache servers, right? So you can do that across multiple data centers too, right? So that's basically what we did here. So this diagram doesn't show it very well, but what you can imagine is, each web box has a Memcache proxy client, which has connections to all of the different Memcache tiers and all of the different databases and all the different data centers, and it's then able to sync up and replicate the deletes to make sure that the caches are coherent in different locations, right? Cool. So that works for San Francisco. Now, we also have data centers in other places. So the challenge with this is that the latency, sorry, this isn't latency. This is a race condition. So the reason why we couldn't have the same solution for this is because you basically get into the situation where you're sending where you also need to sync the databases in addition to syncing the Memcache tiers. So you'd get into this situation where the database would basically replicate by sending over the queries from the West Coast to the East Coast, right, and then executing them. And then the Memcache would sync up, but there would basically be this race condition over which delete came first, right? So that caused issues. So the way that we actually solved this, which I think is a really creative solution, was to, instead of trying to sync it up through having one Memcache proxy run on the web servers, have Memcached proxy run on the SQL server on the East Coast. So you basically get into this situation where you have these type of SQL queries where we've effectively we've modified SQL at this point to support dirty, which really means delete. So just an old thing that we need to get around to fixing. But So modified SQL query, where as part of the SQL query, it'll take this memcache command, it'll send it to Memcached proxy, it'll execute it on the Memcached tier, and it'll stay in sync. So by using Memcached proxy, able to not only just keep the connection count low, which is one of the original things that we tried to do, one of the original goals of the project, but it also is really what made it possible to keep all the Memcached tiers in sync, just all the way across the country. And we'll use this as we continue to roll out more data centers around the world. So kind of cool. So those are just two of the things that I think are pretty interesting examples of just like architectural decisions that we made with Memcache along the way. And there's more if you want to ask some of the folks who made these, who will come up at the end. One of the other things that I just want to talk about is, aside from these large changes and large projects that took months or in some case over a year to build and roll out, there are also just all these optimizations that we're able to make that can seem pretty small. I mean, sometimes they're hard to find, sometimes they're really easy to fix, sometimes they're harder to fix. But because of the scale that we're operating at, they make a really material difference, right? And they're able to save us tens of machines, hundreds of machines, like millions of dollars. So I want to run through a few of them. The first thing that we did was a lot of the optimizations that we've talked about so far have been client optimizations, right? So fixing the clients that it works first, then implementing it in C, then doing Memcached proxy to cut down the number of connections, make it so that it can replicate and be efficient and all these things. At this point, we basically moved to the server and trying to optimize a number of different things. So Steve Grimm is the one who banged these out, and he's there in the back. So the optimizations are both in memory and in CPU. So if you think about how the memory system works for allocation in Memcache, the default that was built in was slab allocation, right? So as opposed to conventional memory allocation, because that's more subject to fragmentation, and obviously, again, if you're building a memory cache, you want it to be used as efficiently as possible. So making it fragment as little as possible is a really valuable thing. So you had slab memory allocation, but the default for the sizes of the slabs were powers of 2, right? So you'd get these chunks that were 256K, 512K, up to 1 megabyte slabs. And what we found was that for the distribution of our data, this was a really bad size, right? So the way that this works, if you have powers of 2 is the chunk size, then something that's 1,025 bytes will waste 1,023 bytes, right? So you basically will lose. So this ended up being about 60% effective and wasting about 40% of the space in the cache, which is pretty lame, right? So just through experimenting and trying to find a better power, we figured out that, and Steve figured out, that by using 1.3 as the power, which computer scientists don't tend to think in powers of 1.3 as much as powers of 2, but basically by optimizing for that, we were able to get 90% of the memory used, which is obviously a big change, right? And you can imagine, when you have thousands of servers and the size that we're operating at, and this is millions of dollars, right, in order to be able to do that. So just kind of thinking outside the box, not thinking in powers of 2, optimizing this, made a pretty big deal. Same thing on CPU. So this is a more of a systems programming thing, but the first version that we had of this, we just used the normal write system call, right? So we'd write the different buffers, and instead, we found that we were just making all these different system calls. So instead, we were able to re-architect the code, and Steve did this as well, to make it so that we just were getting all the buffers and sending them all over with the write v system call instead, using the method that is called scatter gather IO, reduce the number of system calls, and this actually saved 50% of the system CPU time, right? So just kind of using one system call that is a little bit more esoteric than what most people use, was able to, but I mean I think it's clearly meant for this case, made it so that we were just able to save again, millions of dollars, right? Just based on this change. I mean, it took us a long time to figure out that we should do this, and yeah. So, and then, the same thing in user space, right? In user CPU. So, we, the protocol is string, right? So basically, you transmit strings, and we were actually getting to a point where the majority of the CPU was being used just to parse the commands. So, and what the majority of it was in the strlen command, right? Just like as new information was coming in, we were calling that a lot. So just by taking the length of the string and storing it in a variable, instead of continuing to say strlen, we were able to cut this down by a factor of 3, save millions of dollars, right? So, it's an interesting thing, just like it seems like such a simple optimization, but at the scale at which we're operating at, and the number of servers, and you can just figure, this will compound, because we recently just got up to 100 million users. We're ending the year at almost 150 million, and that's just going to continue growing really quickly, hopefully. Just as we continue adding more and more servers, and these things just compound and make a really big difference, right? And it's a really big focus for the company to get this stuff right and make sure that that this is in good shape. So those are two optimizations that were in user land, or application land. So what we found was that we're actually operating at such large scale that it even makes sense for us to get into the kernel and modify some of the network drivers in order to optimize things even more there. All right, so I'm just going to go through a few examples on this, and then we can open up for questions. But there's this interesting change that's happened architecturally since we started working on Facebook, right? So the first set of servers that we had 1 core. Now I don't even think you can buy a server that has only 1 core, right? And the way that Linux manages probably not all, but the majority of network drivers will deal with. I'm out of order. Sorry. Let me give props to the people who did this stuff. So, Mohan, is he here? No, but Tony and Paul are. Tony's not here either. Paul's here. All right. So, okay. So now, the issue that I was talking about was in the majority of the network driver implementations, the network card will raise interrupts to send the majority of the interrupts to only one CPU, right? So you can imagine that as we're using,